right. Hello, everyone. Welcome to our first Astronomy on Tap of the semester. Um, we are really excited to be here, even though it is online. And we are going to give a few more minutes for everyone to come in before we get started. So, as we'd normally say, sit down, grab a drink, but do so from your own kitchen instead of hosting this time. We'll get started in just a few minutes. All right, it's 7:05 now. We're going to give everyone about 5 more minutes to trickle in, and then we will start the presentations, or at least the announcements before the presentations, in about 5 minutes at 7:10. All right, we're going to go ahead and get started now. So first, we have a few announcements about the semester ahead. So we are going to be doing Astronomy on Tap Triangle online all semester. We won't be returning to full steam this semester, unfortunately, but we are really looking forward to getting back there in the future sometime. We are also, next month, our Astronomy on Tap Triangle will not be on the first Tuesday of the month like it usually is, because that first Tuesday is November 3rd, and we're hoping that everyone is going out to vote then. So we will instead be having Astronomy on Tap next month on November 10th, not the 3rd. And then last but not least, for tonight, please feel free to post any questions that you have in the chat on YouTube, and we will try to answer them as soon as we can. There is a bit of a delay between when the speaker says something and when you all hear it in the stream. So there will be a bit of a delay between when you ask a question and when that question gets answered, but we'll try to make it as quick as possible so that we can leave you all feeling satisfied. All right, so our theme tonight is Stars from Beyond the Grave, and we're going to be talking a lot about white dwarfs with two great presentations from Ryan and Josh. I'm going to start us off, though, with a bit of an intro talk about how stars become white dwarfs in the first place. So white dwarfs are a special kind of star, and only a few stars will get there. And in order to explain how all that happens, we have to look at the life cycle of a star. So we'll start off talking about the life cycle of a star. Here we go. So first you have a normal human, and then they get infected and become a zombie, and then the zombie might, nope, sorry, I think I messed up my slides. This isn't the life cycle of a star. Okay, here we go. The life cycle of a star. So this is a bit of a complicated chart, and I promise that I won't show you the even more complicated version that I had to make when I was studying for my finals. But in general, a star is formed from a gas cloud. It becomes a protostar, and then as long as it's big enough, a real star. If it's not big enough, it might become a planet or a brown dwarf. Tonight's not about those, though, so we're not going to go there. This star then will do one of several things, depending on how big it is. And it might end up as a white dwarf right as soon as it's finished its natural life, or it might go through a couple different stages first, or it might not even end up as a white dwarf at all. And I'm going to go into a bunch of detail about these different steps. So the first step in a star's life is a gas cloud. So a gas cloud is exactly what it sounds like it is. It's a big giant cloud of gas somewhere in space. And in this cloud, the hydrogen gas that makes it up is a lot more dense than it is in other areas of space. It might be as dense as about 1,000 particles per centimeter cubed. That's way less dense than any atmosphere you'd find here on Earth, but it's about the most dense that gas gets out there in space. And at that density, there are enough particles running around that they might every once in a while run into each other and stick. And if that happens, and you have enough hydrogen particles running into each other and sticking, that you've got a little clump of hydrogen. And that clump will start getting bigger and bigger until it starts to sort of pull in other particles through its own gravity. And then that clump will grow much bigger until it becomes a protostar. This protostar, it's just that. It's just a big clump of hydrogen. But the center of that protostar is a lot hotter and a lot denser than the outer layers. The way I always explain this to kindergarteners is if you piled all the kindergarteners on top of each other, the one at the bottom of the pile would be really hot and really squished. And that is, more or less what happens with less kindergarteners and more hydrogen. So the center of the protostar is hot and dense. And if there's enough stuff in the protostar pushing down on the center, it'll be so hot and dense that it will start fusing those hydrogen particles into helium particles. And then you've got a proper star. So we've moved from the first stage of our life cycle onto the next main stage of the life cycle. And then this star, depending on how big the star is, it'll go through a couple different phases. So the first stage, star stage 1, I'm calling it, we've got the whole star is pretty much made out of hydrogen. The core is the hottest and the densest, and in the core, that hydrogen is fusing and turning into helium. And then there are the outer layers, which aren't as hot, so the hydrogen there is sort of just hanging out. It's not turning into any helium. While this is happening, while all that hydrogen is turning into helium, it's producing a lot of energy, and it's pushing out on the outer layers of the star, which are pushing in on the core because of gravity. And these inner layer push and outer layer fall, they kind of balance against each other to keep the star stable. And that balance is going to hold as long as we're producing lots of energy in the core, as long as there's hydrogen to turn into helium. But eventually, the hydrogen is going to run out and it's all going to be helium. And as soon as that happens, there is no more energy pushing out on the outer layers, and they were relying on that to stay out, so they start falling inwards, and the star enters what we would call a collapse. So while the star is collapsing, it's going to decide which way it goes. If it becomes a white dwarf, or if it is a large enough star that it's going to do something else. And I'm going to lump these two, medium and large stars, in together in one group for this. But if the star is about the size of our sun or smaller than our sun, it's going to start collapsing and it's just going to keep collapsing. The outer layers, the medium layers of the star are going to fall inwards on the core. The core itself is going to fall inwards and become smaller. And the outermost layers of the star are going to kind of get let go of. And they're going to move away from the star. And this is going to produce a white dwarf. At the end, all you've got left is the little white dwarf core, which, if you remember at the end of our star stage 1, the core of our star was made of helium and the outer layers of hydrogen. So now we've got a white dwarf, the core of which is made of helium and the surface of hydrogen. And this white dwarf is surrounded by all of those outermost layers of it that were ejected off of the star as it collapsed. And this is what we call a planetary nebula. And this is how most of the stars in our galaxy will end their lives. It's how our own sun will end its life, as a helium core white dwarf, and perhaps with a planetary nebula around it. But it's not how every star in the galaxy will end its life. Some stars are so massive that as they start to collapse inwards, the cores of them get so hot and dense that the helium can start fusing and turning into carbon. So now we've got, which is similar to what we had before, where the core was burning hydrogen, but now the outer layers are also hot enough that they're burning hydrogen now too. So we've got two separate types of fusion going on in our star at the same time. The innermost layer, which is turning helium into carbon, and then an outer layer where some of our hydrogen is turning into helium. And this is gonna this process will repeat. The core will burn until it runs out of material, and then it will start to collapse. And then, depending on how massive the star is, maybe the core will get hot enough that the next layer of fusion is going to start. So for the most massive stars, we get something really oniony looking, where the innermost core is burning silicon into iron, and then there are outer layers turning different elements into different ones. With the outermost layer still made of hydrogen turning into helium. And this is what happens to the most massive stars in the galaxy. But these stars will never turn into white dwarfs. So you're going to have to come back to a different Astronomy on Tap to learn what happens to them. And we're going to focus on those stars that only end up with about 2 layers of fusion going, helium in the center and hydrogen on the outside. Because those stars will turn into white dwarfs. So once the helium core is burning, we will start forming a giant star. A giant star is formed because when that helium is burning, it's not producing quite as much energy as the hydrogen was when it was burning at the center. So it can't quite keep up the push that the hydrogen was keeping up, and the core shrinks a little bit. And because the core is shrinking a little bit, it's also losing its grip on the outer layers just a little bit. So they're going to start to expand. Not so much that they leave the star altogether and we get a planetary nebula, but a little bit, which means that our star is going to grow until it becomes a giant star. Also known as like a red giant, or sometimes, if you're being real scientific, an asymptotic branch giant star. But in general, it's a giant star. And at the core of it, we have helium turning into carbon. Then we have hydrogen turning into helium on the outer layers. And this is going to keep happening as long as there is helium in the core. But eventually, the helium is going to run out, and you're left with a carbon core. Then the same thing is going to happen as happened before when we ran out of hydrogen in the core. The core is going to collapse, the sort of inner layers around the core are going to collapse, and the outer layers are going to expand off the star, which gives us our second type of white dwarf. Now, the only difference between this type of white dwarf and the ones we talked before is what the core is made of. Before, it was made of helium because that's as hot as it gets. It only got hot enough to make helium. Now we've got stars that were hot enough to make carbon. So now we have a white dwarf with a carbon core and helium and hydrogen on the outer layers. And it's still surrounded by those expanding outermost layers, creating a planetary nebula. I did promise you a life cycle, and you might have noticed that the life cycle that I showed you was pretty linear. So this is also where the return to the beginning comes in. These expanding outermost layers are made of hydrogen, the same as our gas cloud at the beginning. And these expanding outermost layers might someday end up in a new gas cloud and create a new protostar and start the cycle all over again, which is where the cycle begins. And that is how you end up with a white dwarf. So now I'm going to pass it on over to Ryan to start with, and he is going to tell you all about forensic astronomy using white dwarfs. Ryan is a 4th-year graduate student at UNC. He works with Dr. Chris Clements on studying white dwarf astrophysics. He is a Durham, Chapel Hill native who attended High Point University to get his undergraduate degree in physics and is now back here in Chapel Hill. So I'm going to hand it on over to Ryan.
Thanks, McKenna. I'll go ahead and share my screen so that we can see my presentation here, and then we can get rolling. Let me just make sure that I have the presentation going. Awesome. So, like McKenna said, I'll be working on forensic astrophysics, and we're going to be looking at examining our exoplanet remains using these white dwarfs. So let's dive in. I'm sure we're all armchair forensic scientists. We've seen our fair share of CSI New York and Miami and the like. So what evidence could we collect from a crime scene? Let's see. There's probably blood somewhere, or maybe fingerprints. How about footprints? There's probably hair, unless someone's bald, which is fine. We have possible security camera footage because everything's being filmed these days, and there may or may not be a witness report or a sketch that we could work off of. Now, we can take all of these things, if we're a forensic scientist or a detective, and piece them together to figure out the who, the where, and the what of any particular crime. And when it gets interesting, though, is if we have pattern criminals who go after a certain kind of victim. And all of these guys that you see here have a pretty particular MO. I think it's teenagers trying to have fun. But usually when we're trying to figure out the why of a pattern criminal, we would like to ask the victims, but generally we can't. And so we rely on our medical examiners, our coroners, to tell us what's happened. So what's our parallel to astronomy here? Well, let's take a look. So in astronomy, let's talk about the kind of evidence that we can collect. We had all that evidence from our crime scene for forensic scientists, so we must have something we can look at here. Well, we have light, and well, we just have light. And so that's really what we have to work off of. And I have an asterisk there because recently there's gravitational waves, but that's not really going to be helpful with our objects at the sensitivity that we can detect at the moment, or that I have access to. So for all intents and purposes, we're just dealing with light. Now, we have to be clever because you might ask, what does light even tell us? I mean, I look at a light bulb and it just tells me that it's on. So when we collect our light from a star, it goes into the telescope, and we can be clever by spreading it out with a spectrograph. And this spectrograph spreads light out according to its wavelength. And now wavelength is tied to the energy of the light that comes in. And so short wavelength light is actually going to be higher energy, and longer wavelength light will be lower energy. And so when we spread this light out, we can plot it according to wavelength and intensity and make a map. And this map, or spectrum as I'll call it, will actually reveal the composition of what we're looking at. And so by looking at this spectrum here, I know that this spectrum is a hydrogen spectrum. Why? Well, it says so right at the top. It says hydrogen absorption spectrum. Awesome. Let's say that title isn't there. How would I know? Well, this is a pretty characteristic absorption spectrum of hydrogen. I'll explain why I'm using hydrogen as my example in a moment, but each one of these lines corresponds to an electron orbital in the hydrogen atom, as you can see over here. And so each transition has a certain energy, and that corresponds to a certain line on our spectrum. So to reiterate, in astronomy, our only evidence is light. And so how are we going to use that for our astronomical autopsy? Well, we're not quite done with our background. Because as any coroner or medical examiner might know the human body to a great degree, they're subject matter experts in the human body. We too need to be subject matter experts in our system. And in this case, we're looking at white dwarfs. So we need to be our subject matter experts in white dwarfs. Now, this photo here is a bit outdated. So astronomy used to be done under the stars through an eyepiece, and it was very romantic and wonderful. And these days, I think the romance is still there with astronomy, but it looks a little bit different. Our light gets collected by these telescopes offsite, and really the astronomers are sitting at their computers and analyzing data remotely. And so the astronomy observing room might look a little more something like this, where everyone's kind of logging into their computers and looking at light that way. So that's a bit more accurate these days. But anyway, let's answer two questions to learn more about white dwarfs. What are they made of? And where do they come from? So the first question, what are they made of? McKenna touched on in her intro talk. And so I will only do a quick overview here. And so they have a pure hydrogen atmosphere. There's also variants that have helium atmospheres and everything like that. But here I'm just going to focus on these pure hydrogen atmosphere white dwarfs. And now you see why I was talking about this hydrogen spectrum before. Because if we point our telescope at this white dwarf that has a beautiful pure hydrogen atmosphere, we see just these absorption lines. It's wonderful. However, something like 25 to 50% of these white dwarfs are actually metal polluted. That is, our absorption spectrum changes. And so if a body in space crashes into our white dwarf and burns up, it will deposit its material all over this white dwarf, and our spectrum changes. And now we have all of these lines corresponding to different elements. Metals like sodium and magnesium and silicon and carbon. And so I'll stop here because if you're paying attention, I said carbon and sodium, and I was talking about metals. And so if we remember our periodic table, you're right. I have no idea what I'm talking about unless you remember I'm an astronomer. And for me, the periodic table looks something like this. Everything heavier than helium, I'm just going to call a metal. So if I do that again, that's why. It's because my periodic table in my head is a little bit more messed up. So something that couples with this pure hydrogen atmosphere is the intense gravity of a white dwarf. So we know that these are the leftover cores of these stars, but that means that they must be very, very compact. And so these things have masses close to the mass of our sun, but a radius equal to that of Earth. And so that's really hard to comprehend just how dense that object could be. And so I'll do this for scale. Let's take our astronaut here, and he or she's wearing a very special space suit. And on Earth, this astronaut weighs about 150 pounds. Let's put this astronaut on the surface of the white dwarf, and the suit is special now because it can survive burning up on the surface of the white dwarf. And we find that our same astronaut on the surface of this white dwarf weighs 50 million pounds. That is absurd to think about. I mean, Pancake Flat doesn't even describe what this astronaut would look like. So that should give you an idea of how intense the gravity is on from these white dwarfs, because they are so dense. And this intense gravity causes elements to sink. And so we see these pure hydrogen atmospheres because every element that's heavier will sink towards the core of a white dwarf. And so just like in a glass of water, a denser, something that's denser than water will sink to the bottom, and something that's less dense than water will float on top. And that also tells us something about the white dwarf. What? Well, if I see a spectrum that looks like this on a white dwarf, that has to be recently put there, because otherwise everything would sink to the center. And so if I see things like iron on the surface of a white dwarf, it probably came from something else rather than the white dwarf itself. It's not just floating around there on the surface of the white dwarf, probably. So we know a little something more now about what white dwarfs are made of. And so let's think now, where do white dwarfs come from? And this question was answered very thoroughly by McKenna. And so I am only reiterating to phrase or to put into context what we're talking about. We have our main sequence star, planet, possibly more. It could be one, it could be many. Eventually, when this thing goes red giant, this planet gets obliterated if it's close. If it's far away from the surface of this red giant, it may just have its atmosphere stripped away and be scattered away. And so the planetary system around this red giant is being totally decimated. And when this envelope eventually goes away and we end up with our white dwarf no longer fusing any elements, we have a dead star, that is a star no longer fusing, and a completely decimated planetary system. And that gives us our crime scene. And so now we have a victim that we can do our autopsy report on. So let's see what we can find. I want to take a closer look at our victim. And so this is something that we are looking at. And so you have a white dwarf here, and then surrounding the white dwarf is a debris disk. And so this debris is from that planetary system. And about 1% to 4% of all white dwarfs have this debris disk around them. And I put all these images here because it's probably made of a very fine, solid dust surrounding this white dwarf. Even rarer still are white dwarfs that have gas and dust in their debris disk. And so that's less than 1% of all white dwarfs that we know of have gas and dust in a debris disk that's surrounding the white dwarf. So this, when I say a system, this is what I'm talking about, a white dwarf and its gassy, dusty disk. So this is our victim that our pattern criminals are going to be after. And the way we find these systems, our victims, in space is by looking for particular lines in their spectrum, which I mentioned earlier. And that's known as the calcium triplet. And so these three lines will actually show us that we have a gassy, dusty debris disk system, or the victim that we'll be talking about. Now you might say, wait a minute, all the stuff you showed me before was just a single line. It was a point in space. And what we see here is something that looks more like a bat's ears, or even Batman's ears, or Dilbert's boss's hair. This doesn't look like what I was showing you before. I promise you, there's no funny business going on. I'm still showing you light. We're still looking at only light. And so we have to think about how that light is actually coming into our telescope. So I replot here our spectrum of our calcium triplet, and on these vertical lines is the energy or wavelength that we expect this transition to occur. And over here, I have a white dwarf and a gassy, dusty debris disk. Now, let's say that this gas and dust is moving around the white dwarf in a counterclockwise fashion, and we have an observer down at the bottom of the page. So some of this gas and dust and stuff will be coming at us with some velocity as it orbits around its white dwarf. And so this stuff will actually have its wavelength compressed. This light's wavelength will be compressed, and it will show up as slightly more blue or further to the left than we would expect it to in our spectrum. Likewise, on the other side of the disk, some of it's moving away, and we would expect that the light coming from this side of the disk would actually be stretched out and more red. And this is a phenomenon known as Doppler shifting. And I promise all of you have experienced Doppler shifting in your daily lives, but it's probably been with sound. If you've ever been on a sidewalk and a siren has gone by, as it's approaching, you notice it's very high pitch. And then once it passes you, the pitch immediately changes and you end up with a siren at a much lower pitch. And what's happening is the sound waves, as they approach you, are compressed with the motion of that vehicle. And as they are moving away from you, they're actually stretched a little bit by the motion of that vehicle. Awesome. So we know what evidence we're looking for. And we also then need to know how to analyze the evidence that we found on our victim. And just like a medical examiner might use gel electrophoresis to DNA fingerprint and figure out, whose DNA they're looking at, we use a method with these systems by observing them over time. And so I have here at the top one of my calcium triplet lines, and we see that over time they actually slosh back and forth from red to blue and then back again. And so over time we can actually look at these systems, and it tells us something physically about what's happening there. So let's look at some previous systems that have been analyzed. I'll give you the two extremes. So one of these systems, if we look at it over time, the bat ears will go from red shifted to blue shifted and then back again over the course of about 24 to 30 years. So that's one cycle takes about 30 years. On the other end of the extreme, we have a system whose peaks move from red to blue and back again in about 1.4 years. Okay, so these are two of the same systems. They both have gas dust disks, as we can see from our calcium triplet lines, but they're showing very different things. And so why is that? Well, two theories are really supported by these two systems. And one of them says that as the gas and the dust moves around this white dwarf, it will actually precess. And what precession is what's happening in this video. As it orbits, it will slowly start to move to, I guess, in this video, the right. And that will eventually complete a full lap around the white dwarf. And so in that first one, that would take 30 years. So that's one theory as to what's physically happening as these peaks slosh. And then another, supported maybe by our shorter system, is a debris disk that might look like this, where we have our white dwarf, and then our gas and our dust is clumped together in dense pockets where we have more flux and then pockets of lower density with less flux from the light. And flux means basically inbound light. So more light, less light. And so we have two theories and two different systems. And what we need to do is actually look at more of these systems to see which one of these theories is right, or if they're both right, and that explains the big discrepancy. And so from this, we may even be able to learn a little something about what these systems looked like when they were alive. And they may very well have looked something like our solar system, where they eventually have their star that goes white dwarf and busts apart any planets that are close, like Mercury. And stars like Jupiter and Saturn just lose their atmospheres and then come back in later and are torn apart by the white dwarf. And so in order to know this, we need to study more and more of these systems to get a better idea. And so one of the systems that I'm actually currently studying is going with the same approach of looking at these lines over time. And so these peaks, again, are shifting from red to blue and then back again. And as we get more data with this system, we should be able to figure out which one of these theories fits this system. We see preliminary wise that this may be varying on a period of, I don't know, 2.2 years. And that is a much closer to the period of the second system that maybe has those density pockets in its dust disk. But only more observations and analysis will tell us exactly why or exactly what happened to our victim. And in that way, we have basically done our forensic analysis on our dead star systems. And once we figure out which one of these theories works out, we will be able to essentially catch our killer and find exactly what's happening here. And so we can't make an astronomical arrest, but we can at least know what happened. And so that's, I guess, the most closure that we will get there. So with that, I end my talk, and I thank you all for listening, and I'll open up to questions now.
All right, thank you very much, Ryan. We've got one question in the chat so far. What are the typical speeds of the dust and gas in the debris disks?
Okay, yeah, that's a great question. So these are going to be on the order of hundreds of kilometers per second, moving around these gas and dusty debris disks. So that's enough to see an appreciable blue shift or a red shift. If they were moving too slow, we wouldn't see that same shape where we have two peaks. We would see, I guess, more of a line. It might be a little bit wider, but it would still be a line. Yeah, great question.
Another question. Does the brightness of the debris disk depend on the speed?
So the speed isn't what gives it brightness, although a disk that is, I guess, moving around its white dwarf faster would have more energetic collisions between the dust, which may excite more gas and create more gas to send light to us. So in a way, yes. Yeah, I think that's probably the best way I can consider that. Yeah, but in general, if you have more of this light coming out at a certain, or more of this gas emitting a certain energy, you would have greater inbound light.
Cool. I'll ask a question while we're seeing if anyone else has any. So white dwarfs aren't actually fusing anything anymore inside them. So why do they produce any light at all? Why can we see them at all if they're just dead stars now?
Right. Well, because they were they used to be the core of these red giant stars, or a main sequence star like our sun. What they're doing is they're cooling off over billions and billions of years, and it takes so long because they're such small objects. And so you can think of like whenever you have a campfire and the fire is no longer going, but you still see the red embers, and it takes those forever to actually go out. And so you just need to dump some water on it in order to actually, go to bed without lighting the forest on fire. That's kind of what's going on with that white dwarf. So it's still emitting light. It's the residual, I guess, heat. And yeah, Josh, feel free to jump in if you want to add anything there.
Now that's about all I got too. Yeah, you can just kind of consider white dwarfs to be the glowing coals of dead stars cooling off for eternity. They all start off really hot, though. They all start off probably in the tens of thousands of degrees Kelvin. And our own sun, for comparison, is only about 5,500 degrees Kelvin. So many, many orders of magnitude hotter than our sun. And that's another reason that they take so long to cool off. Basically, the age of the universe is the time scale for white dwarf cooling.
Yeah, and I'll actually add on to that too. We would expect that eventually they would cool off and emit no more light. However, because light is our evidence in astronomy, that would be a very difficult object for us to detect.
Yeah, there are some kind of far-fetched theories that these dark white dwarfs that we can no longer detect are maybe one of the potential sources of dark matter, but who knows?
Great question.
Right, another question. Can a white dwarf become a black dwarf? And how long does that take?
Yeah, so that actually builds on the discussion we were just having, and it is a great follow-up. So like we said, that it takes probably the age of the universe for these white dwarfs to cool off. And then that eventually, when they do cool off and they're no longer emitting light, that would be what you call a black dwarf. And so, yeah, that would take something like, some billions of years, tens of billions of years to happen. But because they emit no light, right, then they're very hard to detect. You have to look at their gravitational effect on their host star if they're in a binary system or something like that, with their effective gravity basically pulling on that host star. But yeah, otherwise, I don't know off the top of my head a great method for detecting black dwarfs.
So just to add to that a little bit, I mentioned that it was kind of a far-fetched explanation for dark matter, that it may be composed of these black dwarfs that we can't see. The real reason that they probably aren't is because these white dwarfs are still solid objects that have some temperature. They've just been consistently cooling from when they were at their max up in the tens of thousands of degrees Kelvin, and then sliding down up until they approach the ambient temperature of the universe. But anything that has a temperature in the universe, even if it's super, super cool, will still show some degree of light emission. It'll just be at a really long wavelength. So for instance, we know that the ambient temperature of the universe is about 3 degrees Kelvin, because the actual just background of the universe has a sort of profile associated with it. If you've heard of the cosmic microwave background before, which cosmologists use to extrapolate information about the Big Bang, that's an example of how these things could still emit light just at really long wavelengths once they've cooled down to the point that we can't see them with our actual eyes. Dark matter, on the other hand, doesn't appear to interact with light at all. So that's why it's kind of not a good explanation, and honestly why we can't really gain any traction on what dark matter is, because it doesn't interact with light. That's a pretty big problem.
Cool. We've got another really great question. So colliding black holes emit gravity waves. Can colliding white dwarfs do that too?
Yes. Yeah. So anything with gravity stretches the fabric of space-time. And you noticed in one of my slides here, if I find it, I had the gravitational wells of something like our sun, and then a white dwarf, and then more dense, a neutron star, and then the black hole moving to a singularity. And so white dwarfs are very dense objects, and so they will have a greater stretch on the fabric of space-time. And so if you had two white dwarfs coalescing, that is orbiting slowly, moving in towards each other and then colliding, that event would emit gravitational waves. Just like me moving my fist back and forth really fast emits a gravitational wave. It's just harder for us to detect these gravitational waves from white dwarfs because they're not quite as large as the ones from black holes, and it's already a very difficult medium to detect. It requires a very high degree of precision and background reduction in that experiment to find gravitational waves from black holes. And I imagine with time this technique will only get better. However, at the moment I think it's probably outside of the reach of reasonable detection.
Yeah, so to build on that a little bit, right now we have one gravitational wave detection facility in the world, which is LIGO. And you all have probably heard about that before. LIGO, though, has a disadvantage that it's on the ground. And the way that gravitational waves are measured is due to very subtle contractions in space-time as these gravitational waves are passing through our detectors at LIGO. And so these things need to be tuned to the sensitivity of like a fraction of the radius of a proton or something. It's an insane degree of precision that these two facilities that comprise LIGO need to have in order to confirm a gravitational wave detection. So it's no coincidence that the only ones that we've detected so far have been black hole mergers, where the black holes themselves are on the order of hundreds of solar masses in mass. White dwarfs being on the order of only about one solar mass, or half a solar mass, means that the waves that they produce are far, far weaker. And so LIGO, as it stands now, is not capable of detecting gravitational waves from binary white dwarfs. But hopefully coming in a few years or decades, depending on the time scale at which NASA moves, there is a proposed new system called LISA, which is going to be out in space. And LISA stands for Laser Interferometry Space Array or something like that. It's essentially going to be a triangle of satellites that have a laser beam connecting the three of them. And so because it's not sitting on the ground, it's not going to be subject to, earthquakes or seismic activity on the Earth's surface or cars driving by or something like that. It'll be really stable and out in space, and it should be able to detect things that are more towards this low amplitude regime that we expect white dwarf binaries to produce.
Yeah, well said. An excellent question also.
All right, I'm going to give it about 1 more minute to see if anyone else has any questions. But while we were waiting for that, Ryan, if you haven't told us already, what's your favorite fact about white dwarfs?
Let's see. I like that they take forever to cool off. I talked about that campfire analogy, and I think if you know me, you know that I can sit and stare at a campfire for ever and just not talk and just be locked in. And I like that they have that slow cooling off for what has already been an eternity, right, in the frame of our universe. And I don't know, that's just pretty neat to me, I guess. And they happen to be really convenient when you're trying to study the things that are falling onto them, which you all know now.
Awesome. All right, so our next talk is by Josh. Josh is a 5th-year PhD student at UNC, working alongside Ryan under Dr. Chris Clements. His research focuses on white dwarf mergers and their remnants, and he's also learning spectrograph design from Dr. Clements. He did his undergraduate at Colgate University in upstate New York with a double major in astrophysics and philosophy. Josh is surviving the pandemic with his wife and 2 cats and a well-stocked bar. So I'll hand it on over to Josh.
All right, thank you so much, McKenna, for that introduction, and Ryan for a fantastic talk. So I'm going to tell you a little bit about a new class of system, which we sort of helped kick off within the past year right here at UNC. So it's some exciting new astronomy being done right here in the Triangle. And continuing with the sort of spooky Halloween theme that we've been doing, I'm going to tell you about how these dead stars, the white dwarfs that Ryan and I study, can be electrically sparked back into activity due to the presence of a planet orbiting around them, potentially. So these are a sort of electric generator in space, like how Frankenstein was electrified back to life. These white dwarfs are experiencing the same thing. So First, a little bit of background about how we discovered these objects. I'm going to skip over most of what Ryan talked about with regards to spectroscopy in the previous talk and focus on what is relevant to this particular research. We heard from Ryan that you see a spectrum from an object which is emitting light. When that light passes through a spectrograph, the prism splits it out into its component wavelengths. And a lot of stuff in the spectrum can tell us information about the physics that's going on in that star. So if we see a continuous spectrum like Ryan showed us in the previous one, where you have emission at all wavelengths and there's kind of an overall curve shape to the spectrum, that tells you that that spectrum is being generated due to the temperature of the object that you happen to be looking at. So this is generally the case for stars. If you look at the shape of their spectrum, just by looking at where the peak of that curve is across all wavelengths, you can get an idea of the temperature of the star. But you get these absorption features that we saw in the spectra that Ryan showed by having a cooler gas in between you and the source of the continuous emission. And the reason that you get those dark lines that comprise the absorption spectrum is because as that background continuum light passes through the cooler gas of a nebula or something like that, a gas cloud, the elements that are composing that gas cloud will suck up photons that correspond to particular energy transitions in the electrons around that star or around that element. And so, for instance, if the gas cloud is composed primarily of hydrogen, when the continuum light of a star passes through the hydrogen cloud, you'll get hydrogen absorption features. And so that will be the signature, the forensic signature that Ryan talked about that you get in your absorption spectrum. In contrast, though, if you are looking at that same gas cloud that's been absorbing light from a background source, but you are not looking through to where the background source is behind you. So basically that gas cloud that's absorbed some light from a star is the hottest thing you're looking at. You'll instead see emission at those exact same wavelengths that the cloud absorbed the continuum light, because it's basically now just de-exciting all of the electrons and spitting off these photons that it sucked up in all different directions. So the emission spectrum is sort of like the inverse of the absorption spectrum, basically. And in order to get an absorption spectrum, you don't necessarily need to have your cooler gas separated from the source of your continuous emission. A lot of people don't really consider it, but stars actually have atmospheres, much like our own planet does, much like Earth does. And we know from traveling around in airplanes and such that, down on the surface of the Earth here, the ambient temperature of the atmosphere is pretty balmy, pretty comfortable. We're able to live here. But as you go further up into higher layers, there's a temperature gradient. The temperature begins to drop as you increase in altitude going out in the Earth's atmosphere. And the same thing is the case for stars as well. So there we go. So here is a typical hydrogen atmosphere white dwarf spectrum. It looks a lot like the one that Ryan just showed us in his presentation. And the reason that we only see the signatures of hydrogen here is because hydrogen is composing that coolest outermost layer of the white dwarf atmosphere in this case. And like Ryan explained in his presentation, the reason that we only really see the signatures of hydrogen is because white dwarfs have such strong surface gravity that they very rapidly stratify elements that compose their atmosphere. So the heaviest elements will tend to sink down very quickly, and you're left with only the lightest stuff on the outside, which typically is, your hydrogen or helium, something like that. So yeah, that's how you produce a typical white dwarf spectrum and what you can learn about it. You can learn about its temperature, its composition, and the composition of the atmosphere in particular. So Ryan talked about how spectral lines can be affected by the velocity of objects. If an object is moving towards you, then its wavelength will be shifted towards the blue, and in contrast, if it's moving away, its wavelength will be shifted towards the red. That's but one physical thing that can affect the appearance of a spectral line within a spectrum. Another thing that can affect how a spectral line looks is magnetism. So what happens with a magnetic field is that it interacts with the angular momentum of electrons that are creating these spectral lines. And because these electrons can have different orbital angular momentums, when they interact with a magnetic field, it tends to split them into different levels depending on how many potential angular momentum configurations there are. I'm not going to go too much into that because it gets really deep into some quantum physics. The takeaway here is pretty much just if you are looking at an undisturbed elemental signature, you'll see one line. And if you flip on a magnetic field, it'll split that line into multiple components. So at first order, it could be 3 components. It could be 5 components, depending on what kind of spectral line you're looking at. And this video here on the right is kind of showing you that. I'm sure you saw the initial line was just single and solid. And then when they flip the magnetic field on, that line splits into the 3 components that we see here on the right. And we see the same signature in magnetic white dwarfs as well. It's the really easy way that we can pick out the magnetic white dwarfs from just all the rest when we are looking at a big sample of different stars. So we saw back in the 40 Aries C example 2 slides ago that all of those hydrogen absorption feature cores were really sharp and precise. But when magnetism plays a role, it splits that core into the Zeeman components. And so by measuring the separation of these split features, we can do some physics and calculate the strength of the magnetic field of this white dwarf. And then I also mentioned emission spectra back on the spectroscopy slide. Just a quick mention, white dwarfs do also exhibit spectral lines in emission. However, it sometimes takes a little bit of a special situation to make this occur. You'll remember that I mentioned before the reason that we see absorption lines coming from stars is because the outer layers of their atmosphere are cooler than the surface where the light is being emitted. So the light is coming through a cooler gas and imprinting that chemical signature of the cooler gas onto the spectrum. But in order to get emission, you need to have a site on the white dwarf that is actually hotter than the white dwarf surface underneath. And that's a little difficult to do with white dwarfs because, as I mentioned before, they tend to be very hot in the tens of thousands of degrees Kelvin. So one particular case where we do see emission in white dwarf spectra is a system known as a cataclysmic variable. And that's the little artist rendering that I have here on the right. So a cataclysmic variable is basically a binary star system where one is a white dwarf and the other one is a main sequence star or a giant star. Doesn't really matter, just as long as it's of lesser surface gravity than the white dwarf. And they come close enough together so that the white dwarf's intense gravity starts to strip off the atmosphere of that main sequence companion. And that material can form into a disk, much like the debris disks that Ryan just talked about in his talk. And this material can also fall onto the white dwarf surface, much like that remnant planetary material. And as it falls onto the surface, you get this kind of instantaneous burning where these elements are burned as they hit the white dwarf surface, and it's hotter than the actual just ambient surface of the white dwarf. And so because of that, you see all of these lines in emission that you see in the spectrum here on the left. But these are actually going to be typically associated with the composition of the donor star rather than the white dwarf itself. So bringing this to the whole point of my talk, these sort of electric generator systems, these were first discovered back in 1985 with an object called GD356. And GD356 was interesting because its spectrum pretty much only shows H alpha and H beta, the two first lines in the Balmer series, which is the hydrogen element series. And those two features are both in this Zeeman split emission. You can see the triple peaks at both H alpha and H beta here. But the confusing thing about GD356 is that it did not appear to have another stellar companion with it. So if you can't explain how it's getting emission lines in its spectrum by material falling onto the surface of the white dwarf and burning really rapidly and outshining the surface underneath, how do you get emission lines on an apparently isolated white dwarf that doesn't seem to be interacting with anything? So this object was discovered back in 1985, and a lot of papers were written across the 35 years since then, speculating as to what could be causing this phenomenon. But GD356 was kind of its own little anomaly in the white dwarf field for quite some time, up until just last year, when our research group here at UNC discovered SDSSJ 1252-0234. So this star, with its long name, we initially wanted to look at because it was very rapidly variable. And what I mean by variable is if you just took note of its brightness over time, it appeared to be changing in brightness with a semi-amplitude of about plus or minus 5% on a very rapid time scale, every 317 seconds. So basically every 5 minutes, this thing would increase in brightness by 5% and then drop in brightness by 10% and then return to that middle, just ambient flux yet again. And that was really out of the ordinary for white dwarfs. There's really only two potential mechanisms that could explain such rapid variability in the white dwarf, and that's pulsation and rotation. We were pretty easily able to rule out pulsation for other reasons. I'm not going to go into much detail with that. But we figured that given this rapid time scale, it was most likely that this variability we saw was associated with the rotation of this white dwarf star. And what we thought was that there's likely a magnetic spot on the surface of this star, which is rotating in and out of view. And that is what is generating this photometric change that we see. So spots form on white dwarfs due to magnetism in pretty much the exact same way that sunspots form on our sun. We've observed those before. Magnetic field lines suppress convection, so they don't let you dredge up hotter material from deeper in the star's envelope and bring it to the surface. So it creates kind of a dark spot where the material is just kind of sitting there being ambiently cool compared to the rest of the surface. And so as this white dwarf rotates, if the spot is on one point on its surface, when it turns toward us, now we have this dark spot, which is obscuring a significant portion of the star as we're looking at it. And so its brightness will drop as that spot rotates into view. And then as the star keeps rotating, eventually that spot will be on the backside and its brightness will increase again up until it reaches its peak. So the fact that we were already looking for magnetism told us that something weird was going on in this star, as did its rapid rotation. So the last thing that we did once we were collecting our data was to take some time-resolved spectroscopy of this object, SDSSJ 1252. And we found that the rapid photometric variability actually did correspond with spectral variability on that same 5-minute-ish time scale. And the continuum shape appeared to be kind of wobbling up and down, which makes sense. If a cooler part of the star is rotating into view at some point, it was actually changing the whole shape of the continuum to correspond to that change in the apparent temperature of the object. But most interestingly, we found that looking at the Balmer series, when this star was at its photometric peak, so when it appeared brightest, we saw the Balmer series in absorption like you would expect from a typical hydrogen atmosphere white dwarf. But when it reached its photometric minimum, basically when you were looking right down the spot, the Balmer features smoothed out and went away and turned into this triple peaked Zeeman split emission that you see in the animation here on the right. And so this ended up being the second object in 35 years since GD356 to also show this Zeeman split emission in hydrogen. And so the question kind of came back to the forefront at that point: what is going on in these objects? And furthermore, just last week, a third object in this category has been discovered by researchers at the University of Warwick in England. So they found this new star, SDSSJ 1219 plus 4715, and it also shows the Balmer series and Zeeman split emission, though their H alpha looks much cleaner than and similar to our H beta and the ones in GD356. Their H beta, for some reason, is just a complete mess. I am not really sure what's going on there, and I don't think they really were in the paper either. But that really nice, pretty splitting you see on the right at H alpha suggested that there are now 3 objects that belong to this class. So since GD356 was discovered 35 years ago, now this whole class is kicking off as a potential source of interest in the white dwarf community. So we have to explain what is going on and what is causing this strange behavior. And actually, to explain it, we are going back to some very early physicists, in particular Michael Faraday. In 1831, Michael Faraday invented one of the first electric generators, which he called the homopolar generator. And it works very simply based on an equation which you probably learned in your intro physics classes in high school, where electric force equals QV cross B. Q is charge, so you need charged particles to generate an electric force. V is velocity, so you have to give those charged particles some movement. And then if they're passing through a magnetic field B, that interaction is what drives an electric force, which will move charges around on the surface. So I've got a little video on the right here showing one of these things operating. And basically all you do is turn the crank. Your turning the crank is imparting a velocity onto the metallic charged plate at the center. So you are giving the charged particles their velocity by turning the crank. And by having a bar magnet sandwiched on one side, you're also having them move through a magnetic field. So as you continue to turn the crank, as we see in the video here on the right, it lights up the light bulb because there are leads connected to that conducting plate as it's turned, and they carry the current that's generated by this force to a light bulb and cause it to glow. In these white dwarf systems, it has become the prevailing model that pretty much the exact same physics is happening as Michael Faraday's 1831 little handheld electric generator. But instead, what's playing the role of that conducting plate that you turn with a crank is a planet, which is theoretically conducting in some form. So the white dwarf, we already know, has a strong magnetic field. And if there's a conducting planet moving through its magnetosphere, you have a Q because it's conducting, it's got free charges, a V due to the orbit, and a B due to the white dwarf star. And so a current is generated in these systems as well. And this current travels along the magnetic field lines of the white dwarf, ultimately connecting just above those magnetic spots where all of the magnetic field lines meet on the white dwarf surface. And because the white dwarf atmosphere is presumably less conductive than a rocky planet or some kind of conducting planet, you get your dissipation of energy in the atmosphere of the white dwarf, and it glows up into emission, pretty much exactly like that light bulb that we saw in the video on the previous slide. Now, this sounds kind of far-fetched that, the universe was replicating an invention by, man Michael Faraday in 1831, but out in space for all this time. You really don't have to go that far, actually, to see this mechanism in action. All you have to do is go to Jupiter within our own solar system. So Jupiter is known for having a particularly strong magnetic field for the planets within our solar system. And that magnetic field actually does quite a bit to protect us here on Earth from asteroid impacts. So always, thank Jupiter that we're not being hit by an asteroid this year. It would not be out of place for 2020. Yeah, so in the Jupiter Io system, this exact same mechanism is operating. Io is orbiting through Jupiter's magnetic field and driving this electric current, which connects at the poles of Jupiter. And it actually drives a small aurora, which can be detected in some longer wavelengths. So we think that this is what is happening in these 3 white dwarfs, GD356, SDSSJ1252, and SDSSJ1219. But the question which remains is, because this is such a new sort of class of objects that's been discovered, there was basically one of them for 35 years, and now we have 2 and 3 within the span of a single year. We're still trying to figure out how these systems are created. And there are kind of 2 prevailing models for it, and I'm going to colloquially call them the Frankenstein model and the Dracula model. These are not written in the literature anywhere, though I really wish they were. Maybe I'll make that a goal of mine if we happen to come across another one of these. But the distinction is this. For the Frankenstein model, We think that the way that this system was kicked back into life was due to a merger of two white dwarfs. Now, McKenna mentioned my intro. I'm interested in white dwarf mergers. That's the topic of my thesis. And that's why I kind of honed in on this object once we discovered it. So the so-called Frankenstein model works. You have two white dwarfs, which are in a binary, and they are inspiraling to each other due to gravitational wave emission, like we just mentioned in the Q&A in the previous presentation, until they get close enough that the lighter white dwarf starts to become stripped by the heavier one, just like in the cataclysmic variable, where the white dwarf was stripping its main sequence companion. A lighter white dwarf can also be stripped by a heavier white dwarf if it's in a close enough binary system. And it could be the case that it fully disrupts that white dwarf companion and rips it apart until it eventually forms into a debris disk around the white dwarf, the more massive white dwarf. And that more massive one may accrete some of this material and turn into a moderately heavier white dwarf than it was initially. That could also kick up a magnetic field in it, which is necessary to explain this electric generator phenomenon that we saw. And the theory then is that this disk of material from that destroyed white dwarf will cool and begin to form into conducting planetesimals. So first it'll start with small little dust grains, and then dust grains will stick together and form larger pieces, and then little rocks, and then eventually working their way up to planets. And so we're left with a system that is a heavy white dwarf with a strong magnetic field and a rocky planet around it. So it's kind of raising this planet from the dead of its companion that it consumed in this merger process, and then that is driving the electricity in the generator that we see. So that's why I called it the Frankenstein model, because it's rising from the dead to create this energy. In contrast, the so-called Dracula model, which was put out by the authors of that paper that was just released last week, they think that this whole phenomenon was kicked up by the presence of a gas giant planet that may have survived the late stages of single stellar evolution. Now, Ryan mentioned this in his presentation, that those inner rocky planets, when a typical star goes into its red giant phase and swells up, will probably be completely destroyed. But planets that are sitting further out, like gas giants appear to do in general, just using our solar system as an example, the gas giants are all out, Jupiter and past that. The star does not swell up enough to consume those in the red giant phase typically. And so it's possible that a gas giant could survive that and still be remaining around a white dwarf afterwards. This gas giant starts to fall into the white dwarf for whatever reason until it gets close enough that the white dwarf can strip the atmosphere of the gas giant itself. And this can potentially spin it up as well, just like accreting the companion in the previous model. And then we know from studying Jupiter that at the center of Jupiter, even though it's a gas giant, it's got a very thick atmosphere of lighter gases, but the center is this strange material called liquid metallic hydrogen. And it's basically incredibly dense hydrogen that is formed into a new state of matter where it's incredibly conductive, and it's got these weird metallic properties, lots of free electrons flowing around. So this stripped gas giant and its liquid metallic hydrogen core can operate in the same as that supposed rocky planet that rose from the corpse of this other white dwarf in the Frankenstein merger scenario. So I call that the Dracula model because the planet is always there. The white dwarf just sucks away its atmosphere, and that is what gives it life. So Frankenstein and Dracula models. There are some pros and cons for each of these. On the Frankenstein side, there are a number of things that we need to explain from the limited sample that we have so far. First, we have to potentially explain the really rapid rotation period for SDSS J1252. And the merger scenario gives us a really nice way to do that because, two white dwarfs spiraling into each other, they already have a whole lot of angular momentum in their system. So if you just conserve that during the merger, it should spin up the remnant single star after the merger and give it a rapid rotation period. The second thing we need to explain is the strong magnetic field around that remnant white dwarf. This is a particularly interesting subject because this paper that I've cited here, Tout et al. 2008, they were curious as to what gives white dwarfs that have abnormally strong magnetic fields their fields in the first place. And so they looked at a sample of about 1,500 systems that involved a white dwarf and a main sequence star, and they are in a detached binary, which means that there's never been any interaction between the main sequence star and the white dwarf. So there's no transfer of material that's happened in the past. So you can't use that to explain how it could have kicked up a magnetic field or started to spin up. And they found that of this 1,500 object detached binary sample, none of the white dwarfs exhibited magnetic fields above about 2 megagauss, which is their cutoff for strong magnetism. And all 3 of the objects in our generator sample have magnetic fields above that. They're ranging from about 5 to 19 megagauss. So it appears, well, one would assume in a detached white dwarf main sequence binary that white dwarf formed just from single stellar evolution. That used to be just another main sequence star that had a main sequence star as its companion, and that one died first, and that's why there's a white dwarf there. And because they're detached, you figure they haven't been interacting. So that kind of suggested that of this huge sample of 1,500 systems, if they didn't find a single one that had a strong magnetic white dwarf in a detached binary, then maybe magnetic fields are only created through mergers or dynamical interactions of some form. So the merger scenario gives us a way to explain that too. A con, though, on the Frankenstein model side is that, like McKenna mentioned, the compositions of white dwarfs are typically fairly light elements. So it's going to be mostly hydrogen and helium. Some heavier white dwarfs will have a decent amount of carbon and oxygen, but rocky planets are not composed of only hydrogen, helium, carbon, and oxygen. You need things like silicates, the stuff that Ryan sees in his spectra of the consumed planet disks. And so if you have this material that you're positing was thrown off during the merger that then cools to form planets, it doesn't seem to be the right composition to create a conducting planet in the end. So that's a weakness for the Frankenstein model. On the Dracula side, the spin up can be explained by the accretion of the gas giant atmosphere. There's been at least one paper that shows that they anticipate rotation rates on the order of what we saw in J1252 just from accreting the atmosphere of the gas giant planet. Another pro in this sense is we have seen gas giants orbiting white dwarfs. So there was a little bit of a question before is, could a gas giant planet survive the late stages of stellar evolution? And we have observational evidence that yes, that is the case, because a gas giant has been observed orbiting a white dwarf just last year. But the problem on the Dracula model is that it's not so easy to explain the presence of that strong magnetic field, because as we saw from the Tout paper, it doesn't appear that strong magnetic fields can form from single stellar evolution. And just accreting a gas giant atmosphere, it's not exactly clear that that's enough to generate an entire magnetic dynamo mechanism within the core of a white dwarf, which is such a dense physical object. So that's a weakness on the Dracula side. Both have their pros and cons, and the only way to answer this is going to be more research needed. Like I said, there was only one of these for 35 years, and then 2 of them were just discovered within the past year. So this is kind of a burgeoning new field of white dwarf astronomy that started right here in Chapel Hill. So yeah, thanks so much, and I'll take some questions.
All right, we've got one question. What would the conditions on a planet around a white dwarf be, and would it be possible to have life on such a planet?
Yeah, that's a really interesting question. GD356, I mentioned that a whole bunch of papers have been published in the meantime trying to figure out what was going on with it. And at least one of them, they took a whole bunch of photometry out in long wavelengths where you might see the signature of a cool object like a planet orbiting it. So basically the way that we can tell if a white dwarf is isolated or not is if you take measurements across many wavelength ranges from the X-ray and UV all the way through visible and down to infrared, microwave, and radio. The general shape of that curve should tell you what objects you're looking at. And if a white dwarf is in a binary, or if it has a planetary companion, you may expect to see a little bump once you get to long wavelengths out in the infrared and microwave. And that's due to the presence of this cooler object, which is also hiding there and contributing light to the system as you look at it. That paper that looked at GD356, it had pretty decent photometry coverage out in the IR, but the best that they were able to do for a planet constraint was that they didn't think it was any more than about 12 Jupiter masses. And I know that that's not really helpful. We've seen gas giants that are on the order of Jupiter, up to tens of times Jupiter mass. And then you even start to enter kind of brown dwarf territory at that point. So brown dwarfs are kind of the weird middle child between gas giant planets and the lightest main sequence stars. So the only constraint observationally that's been put on a potential planet is it has to be less massive than 12 Jupiter masses. And that can mean pretty much anything at this point. And that is about all the information I can give about planet parameters that could be driving these things. As to whether life could survive on these, I will tell you that is almost certainly no. And the reason for that is, well, in the Frankenstein scenario, it's a little obvious that, you know, this was a white dwarf merger that kicked off a whole bunch of material, and then that material solidified into a planet after those stars had already died and gone through this violent merger process. And so it's unlikely that life would have survived that destruction of a planet and then this violent white dwarf merger. And furthermore, with the rocky planet case, in order to even have this system being kicked into activity, the planet needs to be more conductive than the white dwarf. So it's basically, that's how a typical electric circuit works actually, is the filament of a light bulb that lights up when you turn on an electric circuit is a resistor. And so energy is preferentially dissipated there, and that's what causes it to glow. So if a rocky planet is driving this, like in the Frankenstein scenario, it should not have an atmosphere. Because an atmosphere acts as an insulator and would dampen the conductivity of the planet. And it could even bring it down less than the white dwarf atmosphere. So we might expect to see this mechanism turned off if a rocky planet with an atmosphere was orbiting a white dwarf. So it's unlikely in that case. And then in the Dracula model case, just the fact that it's a gas giant planet would suggest that nothing can live on it because it doesn't have a surface. And especially on the exposed metallic hydrogen core, if that is what indeed is driving this mechanism on the Dracula model side, it'd be a bit of an inhospitable place.
Great answer. So we will give it another minute or so to see if anyone else has any questions. But while we're waiting, I'll give you the same question I gave Ryan. What is your favorite fact about white dwarfs?
Yeah, so my favorite thing about white dwarfs is when they blow up. And that was kind of the whole inspiration for my research. It was actually what I did my research on in undergrad too. So the reason I think white dwarfs are so cool is that they can explode in a special type of supernova called the type 1A supernova. And basically what happens there is, so we already know that the white dwarf is just kind of the dead remnant of a typical star. It's not really doing any more activity on its own. But if it can continue to accrete mass from a companion, or if it merges with another white dwarf, and there's enough energy and material in the system so that the merger remnant can't hold itself up anymore, it'll collapse and explode in a supernova. Because you can kind of think of these mergers, well, let me reword that. So because you start with a white dwarf and you gain mass up to the point where it can't hold itself together anymore, you can kind of think of all these explosions as having about the same amount of fuel that goes into the detonation. And so the peak brightnesses of these supernovae are all within a very narrow range. And we can actually disentangle that as well by looking at how the light decays away. And this makes them really useful for measuring distances in the universe. We call them standard candles. Type 1a supernovae are a type of standard candle. Because if you are using a telescope here on Earth and you observe a type 1a supernova, you can figure out how bright it is at its peak by looking at the light curve, and then how bright you see it here on Earth is just going to be a function of how far away it is. So you can use it to measure, use type 1a supernovae to measure distances to very distant galaxies. And in 2011, the Nobel Prize was actually awarded to a group of astronomers who looked at a whole bunch of type 1a supernovae going out very, very far in the universe. And they were able to actually prove that the expansion of the universe is accelerating due to little differences in the brightness they saw as they kept going further and further out into history. So type 1a supernovae are my inspiration. And that's why I've kind of gone towards the white dwarf mergers thread for my PhD research, because that's a potential progenitor scenario.
Awesome. All right, so we've got a couple great questions here. The first one, could this be not a merger, but a very small binary star system in close proximity with a fast orbit, where one is slightly less bright, causing the oscillations in brightness? And it says, for example, the binary HM-CAN3.
Yeah, so that was actually something that we did try very hard to disentangle when we were writing this paper. It's certainly possible that you could have two stars that are of very similar mass and temperature, such that their spectral energy distributions, that's the thing that I explained not too long ago, where you look at brightness across a whole bunch of different wavelengths from X-ray, UV, all the way down to IR and radio. Well, maybe not necessarily radio, that's a bit excessive, at least to IR. And it is possible to create a composite SED from two stars that may be a little similar, and maybe that if you just add their two SEDs together, it could look like single star SED. So we ran a whole bunch of tests on that when we were writing this paper. And what we really found is that the system was a bit too contrived in order to recreate what we saw in the SED, at least for SDSSJ 1252. It would have required two white dwarfs of very high mass that were about the same temperature as J1252 appeared to be in the first place. And typically looking at white dwarf binaries that are known, there are not very many of them that have a combined mass very much above the Chandrasekhar limit. The Chandrasekhar limit is that mass limit at which a white dwarf or at which a star can no longer hold itself together and it explodes in a supernova. And in the case of J1252, it would have required two white dwarfs with a mass of about 1.3 solar masses, so just under the Chandrasekhar limit, all the way up to a combined mass of about 2.1 solar masses. So they would have needed to be pretty heavy in that case. And we don't know of many binary systems that have those parameters. So that was one reason that we ruled it out. It was either that, or it would have had to have a very, very small and very cool white dwarf in there, like was just suggested by the question. The problem there, though, is so we talked about how white dwarfs cool off over time. They also become dimmer when they do that because naturally their light output is related to their temperature. And so we actually have a really, really hard time detecting really cool white dwarfs. This is the topic of research of another person in our research group. He's looking at the coolest white dwarfs to figure out what physics is going on with them. And his sample is very limited because they're really hard to see these things. And so we would have had to suppose that one of these was in the system in the alternate case. But we have a really low detection rate of these just because of how hard it is to see them. And so we could assume that they're much more prevalent than they are, and there may have been one in the system. But again, it seemed a little contrived to assume that when a single star fit really well to the SED that we saw in the first place. So we decided to go with the simplest assumption that this was something on its own. Though you do bring up also another interesting possibility. There are a class of systems called AM-CAN-VEN binaries after the primary the flagship object in this class, AM Canis Fanatici. And those involve a white dwarf binary where one of them is transferring material onto the other one. The lighter mass white dwarf is transferring material, just like a CV. And because the only thing that we really need to kick this electric generator into life is that the white dwarf that has the emission is less conductive than whatever conducting object is moving through its magnetosphere, it's possible that after pulling off enough material so that you have, hotter, lower layers of that donor white dwarf, it becomes more conductive at some point because hotter objects tend to be more electrically conductive. You could strip a white dwarf down to the point that it activates this unipolar generator system as well. So that was something that we kind of talked about as an interesting thought, that maybe even the core of a white dwarf could kick this thing into emission.
That's really interesting. The next question is, could there be a merged Frankenstein-Dracula model with elements of both scenarios?
That's an interesting question. So basically you're saying like, so the merger takes place and it kicks off this disk of mostly hydrogen and helium and light elements. And then maybe a gas giant forms from that. And then it eats the gas giant and you have that metallic core, which is driving it. I feel like that could definitely be possible. I can't really immediately think of any reason to not consider that. Again, more research needed. Hopefully this is something that people take into account once more of these are discovered.
Yeah, it'll be really interesting to see how this sort of progresses as you find more and more of these objects. We'll give it another little bit to see if anyone else has any final questions before for either Josh or Ryan about his talk. All right, well, thank you very much to both our speakers. Those were really interesting talks about what happens to stars after they die. And thank you to everyone who came and watched our talks. We are looking forward to seeing you again in person sometime soon. But in the meantime, we will see you next month on November 10th for our next Astronomy on Tap Triangle.
Thanks, y'all.
Yeah, thanks everyone for tuning in.